Welcome to qnawire.
Called the surge function, and it's equal to some number a times t to the p power times e to the negative k times t power. S is the level of medication in the bloodstream. T is the number of minutes that have elapsed. For this particular surge function, A is 0.01 times t to the p power, where p is given to be 4, and then that multiplies e to the negative kt. K is given to be 0.07, so that's e to the negative 0, or actually 0.07, e to the negative 0.07, e to the negative kt, e to the negative 0.07 t. So we are going to graph this function using Desmos, and then we are going to look for the inflection points and kind of describe what's going on with this surge function at those inflection points. Okay, so using Desmos, I graphed the surge function. Desmos prefers to work with the variable x, so instead of the variable t, which was representing minutes, we're just using the variable x. And since the number of minutes that have elapsed since the injection should be, greater than or equal to 0, graphing this function for time less than 0 really didn't mean anything. So to make the graph look a little less confusing, I restricted this function to being graphed when the number of minutes x is greater than or equal to 0. The goal here is to estimate the time, which would be the horizontal x-axis, estimate the time at which inflection points occur. Now, an inflection point occurs when the second derivative of the function is 0. Basically, it's signals, an inflection point signals when the first derivative will change from increasing to decreasing. If the second derivative is 0, that means the first derivative reaches a maximum point, meaning the first derivative, or the steepness, the slope, if you will, was increasing, reached a maximum point, now will start decreasing. Or vice versa, an inflection point being where the second derivative is 0. An inflection point could also be where the first derivative reaches a minimum. The first derivative is decreasing, reaches a minimum, and then starts increasing. Now, if we're looking for the first derivative to be at a maximum point or minimum point, that means, for example, if we say the first derivative is reaching a maximum, that means the first derivative was increasing, reaches a maximum point, will start decreasing. Well, the first derivative lets you know just how steep the function itself is increasing or decreasing. So if we're looking for where the first derivative is going to change from increasing or decreasing, we want to look for a change in the steepness of the curve. Let me go back to our whiteboard here and give you an idea what an inflection point would look like, just so you have an idea what we're looking for. If I have a function, it's going up steeply, okay, but then at this point, it's still going to be increasing, but at a slower rate, okay, this would be an inflection point. The function is still increasing, but the rate at which it's increasing, as indicated by the first derivative, is changing. Here, the function is increasing at a quicker and quicker rate, so the slope or the first derivative is increasing. And then at this inflection point, the second derivative is 0. The first derivative reaches a maximum. The function itself still increases, but now at a slower rate, because f prime of x now is starting to decrease. So this would be the graph of the function f, and f prime of x would change from, the slope would, at this inflection point, changes from increasing and increasing to where the slope or the derivative is now decreasing. Okay, so f prime of x changes from positive to negative. The second derivative at this inflection point would be 0. So this is what happens at an inflection point. At an inflection point, the function will still be increasing, and of course, this can also be shown for a function that is decreasing through an inflection point. Let me give you a little idea what that looks like. If I so erase that. If I have a function that's decreasing, reaches an inflection point, still decreases, but now at a slower rate. This would also be an inflection point. At an inflection point, the second derivative is 0, and the first derivative changes signs. So here the first derivative is changing signs at this point. Here the first derivative is positive. Here the first derivative will be negative. At this inflection point, the second derivative will be 0. Here the first derivative is negative, and then at the inflection point, first derivative becomes positive, even though the function is still decreasing through that inflection point. So we're looking for a bend or a change in the bend of the curve. That's where these inflection points are seen. Okay, we're going up, but then we change how steeply. You can think of it as concavity, kind of concaved up, and then we start concaving down. Here we're concave down, and then we start at the inflection point becoming concave up. So we can estimate, here you can see that the function is increasing, and then approximately around here, there might be an inflection point right around here at approximately t equals 25, maybe 30. So when t is 30 minutes, the function is still increasing past this inflection point, but not as steeply. Okay, here it's climbing up steeply, reaches an inflection point, and then starts, kind of rounding off. Think of this as concave up till time is 30 minutes, and then concave down. So it's a little hard to see here. If we zoomed in, it'd be a little bit easier. But we have a point of inflection here, and then we have another point of inflection here. Here, the function is coming down, hits the inflection point, and the function keeps decreasing, but now at a slower rate. Okay, here it's kind of concaved down if I exaggerate it. And then at this inflection point here, at approximately 100 minutes, the function changes concavity and starts becoming concave up. So let's go back to our whiteboard and write down those two times. So the two values of t, of course on our graph, the variable is x. The two values of t that are inflection points would be, it looks like when t is 35 minutes, we have an inflection point, and then we have another inflection point when x in the graph, or our variable t, was 100 minutes. So let's go back to our graph and kind of describe what's going on with our surge function at these inflection points. So when t, or in this case x, the number of minutes, the time is 30 minutes, we have an inflection point. So for 30 minutes, we are at this point on the graph. So the surge is increasing rapidly until we reach a time of 30 minutes. And then the surge continues increasing, but at a slower rate. That's what happens. The rate at which it's increasing changes, okay? The surge is increasing and increasing. The rate at which the function is increasing is itself increasing until the inflection point. Then the function, the surge, keeps increasing after 30 minutes, but at a slower rate. Now, when the time was 100 minutes, we estimated there was another inflection point here at 100 minutes. Here, the surge is decreasing rapidly until we reach 100 minutes. That's another point of inflection. And then the surge is still decreasing, but at a slower rate. That's what's happening at those two inflection points.